Okay, I want you to close your eyes for a second. We're going to Tokyo.
Okay.
It's late afternoon, maybe 5 or 6 p.m. You're standing on the observation deck of the Shibuya Scramble Square. You've got the wind in your face, you've got your camera out, and you frame up the perfect shot.
I can picture it.
You've got the sun just dipping below the horizon, burning that deep orange. You see the silhouette of Mount Fuji way off in the distance. And right in front of you, the sprawling, chaotic city skyline of Tokyo. Click. You freeze the moment.
It's a classic image. Yeah, I can see it perfectly.
It is stunning. But here is the question, and this is the question our source material for today throws at us right out of the gate. In that photograph, that single static frame, does everything you see exist at the same time?
See, that sounds like a trick question. It feels like a riddle.
It totally feels like a trick question. My gut says yes. I pressed the shutter. The mechanical curtain opened and closed. Whatever light hit the sensor right then is what I captured. It's a snapshot of now.
And that instinct, that gut feeling that a photograph captures a single moment of, universal now.
Yeah.
That is exactly where this deep dive is going to challenge everything you think you know about physics. Because according to the research we are covering today, that photo isn't a snapshot of the present.
Oh.
It's a collage of the past.
A collage of the past. That's a poetic way to put it, but let's get technical. You mean because of light speed?
Exactly. Think about the distances involved in that one photo, that light from the sun. It took about 8 minutes and 20 seconds to travel through the vacuum of space to reach your lens.
8 minutes?
The light from Mount Fuji, it traveled about 100 kilometers, so that's microseconds. The light from the building next door, nanoseconds.
So wait, what you're saying is I'm holding a piece of paper, looking at a screen.
Right.
And the top of the image is 8 minutes old, the middle is microseconds old, and the bottom is nanoseconds old.
Precisely. You aren't holding a picture of one moment. You are holding a document where the background is literally millions of miles older than the foreground. It's a time capsule that has been flattened into 2 dimensions.
Okay, when you put it that way, sure, I get it. There's a lag. But, and I'm going to play devil's advocate here, isn't that just a technicality? I mean, does it really change how the universe works, or is it just a rounding error we can ignore?
Oh, it matters. It matters more than almost anything else in physics.
Mm-hmm.
Today we're looking at a radical reexamination of how we define space and time.
Okay.
The argument in these sources is that standard physics, and we're talking everything from Newton all the way to special relativity and Einstein, has made a fundamental category error. We have confused the map for the territory.
Confusing the map for the territory. That is a classic philosophical trap.
It is, and to untangle this, the source lays out a framework called the 3 worlds, which I found incredibly helpful because, frankly, once you start talking about relativity, my brain usually starts to melt.
Mine too. So let's break down these 3 worlds. This is the toolkit we need for the rest of this deep dive.
Right. If you want to understand the universe, especially how light and time work, you have to distinguish between 3 specific domains. First up, the mathematical world.
This is the whiteboard world, the world of theory.
Exactly. Pure abstraction. Geometry, logic, equations. In the mathematical world, if you define point A and point B, a line connects them instantly. Time doesn't drag. If you draw a triangle connecting the sun, the earth, and Mars on a piece of paper, that shape exists simultaneously. It's a God's eye view. You see everything at once.
Okay, so that's the ideal. That's the geometry class world. Then we have the second one, the physical world.
The gritty reality. This is where actual processes happen. And the ruler of this kingdom is see the speed of light.
Right.
In the physical world, nothing connects instantly. Absolutely nothing. Everything involves a signal, a delay. It's bound by causal laws and conservation rules.
So in the physical world, if the sun disappears, Earth doesn't know about it for 8 minutes.
Correct. The reality of the gravity changing takes time to travel. And then we have the third domain, and this is where the source says the trouble really starts. The observational world.
The observational world.
This is your retina. This is the camera sensor in Tokyo. This is a voltage meter in a lab. The critical insight from our source is that we never, ever see the physical world directly. We strictly only ever see the observational world.
We only see the report that arrives on our desk. We never see the event itself.
Correct. We see the delayed signals that arrive at our specific location. The conflict, the big mess in physics arises because we try to do physics in the observational world, using data that has lag. But we apply the rules of the mathematical world, which assumes everything is instant.
We treat the delayed data as if it's happening right now. We assume the map is the territory.
Exactly. We act as if we can see the whole board instantly, ignoring the fact that we are stuck in the physical world where information takes time to travel.
The source uses a great term for what we should be doing. They call it becoming an information officer.
I love that title. It shifts your perspective completely. An information officer doesn't look at a report and say, oh, the enemy is attacking right now.
Right.
They look at the timestamp. They say, I received this now, but the attack happened 10 minutes ago at a location 5 miles away.
It's about reverse engineering the truth from the delayed signals. But to understand how we got so bad at this, how we started confusing the math for the reality, we have to go back in history. Way back.
Yeah.
Before we even had the coordinate systems we use today. The source uses this analogy of a sandbar that I thought was brilliant.
It's a great visual. Picture yourself on a beach, maybe a low-tide sandbar.
Yeah.
You find a stick and you start drawing a circle or a triangle in the sand.
Yeah.
This represents the pre-Descartes view of the world.
Pre-Descartes meaning before we had those X and Y graphs.
Right. In the sandbar view, space was defined by the object. You draw a circle. The inside is finite and defined. The outside, it's just the rest of the world. It's vague. It's not the circle.
You couldn't really draw an infinite line in the sand. You'd run out of beach.
Exactly. The object came first. Space was just the container relative to that object. But then, in the 17th century, René Descartes comes along and gives us the Cartesian coordinate system, the XYZ grid.
And suddenly the grid comes first.
Yes. Now, space is this pre-existing infinite scaffolding. It's a mathematical void that goes on forever in all directions, up, down, left, right, and we place objects inside it.
Which sounds great. I mean, without that grid, we don't have calculus, we don't have engineering, we don't have the GPS in our cars.
It's an incredibly powerful tool. Civilization runs on it. But the source argues it created a trap for physics because the grid is abstract. It belongs to the mathematical world. It's instant. If I change a number at coordinate 10, 10, 10, the mass changes instantly. We started assuming the physical universe worked the same way.
And this leads to what the source calls a geocentric trap. But they aren't talking about the old idea of the Earth orbiting the sun, right?
No, it's a mathematical geocentrism. Think about how we set up a physics problem on a blackboard. We usually say, let's put the observer at the origin, at 0, 0, 0. By doing that, we subconsciously treat the observer as the center of the universe.
Yeah.
We align the entire infinite grid to that one point.
It creates this illusion that now, at my location, at 0, 0, 0, is the same thing as now everywhere else on the grid.
Exactly.
Yeah.
It smuggles that mathematical world instant connection thinking into a physical world that is strictly limited by the speed of light.
Right.
To prove how messy this gets and to show why this information officer mindset is so vital, the source brings up a thought experiment involving the North Star.
I really like this part. This is where the visual of the three worlds finally clicked for me.
Let's walk through it. We are going to deploy our information officer. We are going to station them all the way out at Polaris, the North Star.
Okay.
So they are hundreds of light years away. And they are looking back at our solar system with a super telescope.
Yeah.
Specifically, they're watching the sun, the Earth, and Mars.
Okay, so we have a triangle in space. Sun, Earth, Mars.
In the mathematical world, that abstract instant world, at a specific moment, let's call it time zero, those three bodies form a very specific rigid triangle shape. They exist there right then. That's the physical reality of where the mass is located.
But the observer at the North Star, they don't see that triangle.
They physically can't. Because the distance from the sun to the North Star, the distance from Earth to the North Star, and from Mars to the North Star, those distances are all slightly different.
And Earth and Mars are moving. They aren't standing still.
Moving fast. So the light that arrives at the North Star now left Earth at one time, left Mars at a different time, and left the sun at a third time.
So the observed triangle that the North Star sees is a phantom. It's a distortion.
It is a shape formed by simultaneous arrival, not simultaneous existence. Mars might have moved millions of miles since that light left. Earth has moved. If you, as the observer at the North Star, assume that the shape you see is the shape that exists right now, you are strictly wrong.
You're confusing the observational world with the mathematical world.
Exactly. The information officer's role, and the role of a good physicist, according to this source, is to say, I see Earth at point A, but I know light took X amount of time to get here, so I need to calculate back. Earth is actually at point B. You have to separate the map you see from the territory that exists.
The source takes this geometry even further. It introduces this concept of the window and the sphere of the past. This got a little technical in the reading, but the visual is actually pretty cool if you break it down.
It is. Imagine a giant bubble expanding out from our observer at the North Star. This bubble represents the sphere of equal past. Every point on the surface of this bubble is exactly the same distance away in terms of light travel time.
So if the bubble is 10 light years big, everything on the surface is from exactly 10 years ago.
Right. Now imagine a flat sheet of glass slicing through space. Let's call that our window of observation. The source argues that measurement, what we actually see and record, is the intersection of that growing bubble and that flat window.
We don't see space as it is. We see the slice where the sphere cuts the plane.
It's a curved slice of history projected onto a flat view. And this leads the source to a pretty heavy critique of modern cosmology. They actually take shots at the idea of the expanding universe.
I noticed that. They suggested that talking about the universe getting bigger might be meaningless.
Meaningless without an external measuring stick. The argument is this. If the universe is expanding, and your ruler inside the universe is also expanding at the same rate, can you measure the expansion?
It's like being in a room where everything, including you, doubles in size instantly. You wouldn't notice a difference because your reference points all change too.
Precisely. The source suggests that what we interpret as expansion, or even things like Lorentz contraction and relativity, where things get shorter as they move fast, might just be perspective effects. They might be artifacts of how we map these delayed signals onto our grid, rather than physical changes in the size of the object itself.
Which brings us back to that sunset photo in Shibuya. The source calls it a surface of equal arrival.
Right. The photo isn't a slice of now. It is a record of photons that all happen to cross the finish line at the same instant, despite starting at different times.
And this is where we have to talk about the elephant in the room. This is the controversial part. The source uses this logic to go after the standard interpretation of special relativity, specifically the famous light clock experiment.
This is the part that might make some physicists spill their coffee.
For those who haven't sat through a physics lecture in a while, or maybe never have, give us the light clock 101. What's a standard story?
Okay, this is the classic Einstein thought experiment.
Yeah.
You have a train moving past a platform. Inside the train, a beam of light bounces from the floor directly up to the ceiling.
Simple enough.
Yeah.
A vertical beam.
Inside the train, the passenger sees the light go straight up and down, a vertical line. But to the person standing on the platform outside, the train is whizzing by. So they don't see a vertical line. They see the light travel a diagonal path up and forward.
Because the ceiling moved while the light was traveling.
Exactly. And because the diagonal path is physically longer than the vertical path, and because the speed of light must remain constant for everyone, standard physics says time itself must slow down for the person on the train.
The seconds have to get longer to allow the light to traverse that longer diagonal path at the same speed. That's time dilation.
That is the textbook explanation. But our source calls foul on this. They call that diagonal line a phantom trajectory.
Why? If the train moves, doesn't the light move with it?
This is the crux of the argument. The source argues that when we draw that diagonal line on a piece of paper, which represents the track frame or the mathematical world, we are doing that thing again. We are confusing the map with the reality. We're drawing a line from coordinate 00 to coordinate 1110 and assuming the light travels that path on the grid.
But the source says light doesn't work like that.
The source argues, moved relative to what? Light spreads out as a sphere from its source. It expands in a bubble. It doesn't care about the train's motion or the track's coordinates. When the light leaves the floor, it's a ripple in the electromagnetic field.
So the error is in the drawing.
The error is forcing a God's eye view grid onto a physical process. The source claims that by drawing a specific diagonal line, we are inventing a geometric path that assumes the track frame and the train frame share a simultaneous now. We're assuming we can see the light being at those different points instantly.
And since we can't, since we're always the information officer dealing with lag,
the source calls this shooting at a moving target. They use an analogy of deflection shooting in 19th century ballistics.
right, trying to hit a moving ship with a cannon.
Imagine the 3 steps. Step 1, you aim where the target was when you saw it. You fire. You miss because the ship moved.
Okay.
Step 2, you aim where the target will be based on its speed. You calculate the trajectory, but you still miss.
Why? Because you didn't account for the travel time of the bullet.
Exactly. Or in this case, the travel time of the light signal coming from the ship to your eye. They fail to account for step 3, the meeting point of the signal and the observer. The source argues that the light clock experiment, as usually drawn, ignores the specific viewpoint of the observer. It ignores the North Star perspective.
So if we accept this view, instead of time physically slowing down, instead of the passenger aging slower than the person on the platform, what's actually happening?
The source suggests that Lorentz transformations, the heavy math behind relativity, are actually perspective corrections.
Perspective corrections, like visual distortion.
Think about looking at a circle from an angle. It looks like an oval, right? It looks squashed.
Sure.
Did the circle physically get squashed? Did it change shape? No. Your perspective changed. The source argues that Lorentz transformations are like converting a curved arc to a flat angle. We are correcting for the fact that we are receiving delayed information from a moving object.
So time dilation and length contraction aren't magical physical changes to the fabric of reality. They're just the math required to make sense of delayed signals.
That is the claim. It's treating the speed of light not just as a speed limit, but as an information horizon. We invented space-time, this complex bending thing, to fix a geometry error caused by ignoring the delay.
That is a lot to process. It basically flips the script on 100 years of physics. It feels almost too simple, doesn't it? Like, oh, we just forgot about the lag.
It does seem deceptively simple, but the implications are huge. It moves the complexity from the structure of the universe, curved space-time, bending dimensions, to the structure of observation. It says the universe might be simpler, Euclidean, flat, maybe even boring. But our view of it is incredibly complex because of the light speed lag.
It reminds me of looking at a Stars and Stripes flag through a rippled glass window. The flag is straight, but it looks wavy. We spent 100 years describing the physics of the wavy flag instead of realizing it's just the glass.
That is a fantastic analogy. We have built a physics of the observation, not a physics of the object.
So let's bring this back down to Earth, or back to the North Star. What does this mean for us, the listeners? Why should I care if my sunset photo is a collage of the past? Does it change how I live my life?
I think it does. It changes your relationship with the present. It means we need to be incredibly humble about the concept of now.
Now isn't global.
Now is a purely local construct. Your now is different from the sun's now and different from the now of the person listening to this deep dive. We are all trapped in our own little bubbles of the present, receiving postcards from the past.
We really are like that information officer. Or maybe archaeologists.
Archaeologists of light, that's a beautiful way to put it. We are piecing together shards of different eras, 8 minutes ago from the sun, years ago from the stars, nanoseconds from the coffee cup on your desk. We stitch them together to reconstruct a present that we can never actually see directly.
It changes how I look at that sunset photo. I'm not freezing time. I'm collecting history.
You are documenting the arrival of information. You're capturing the point where the sphere of the past intersected with the window of your camera.
So here is the big question to leave everyone with. The source poses a challenge, and it's a bit of a brain burner.
It is. The challenge is this. Physics for the last century has been built on this XYZT grid, a God's eye view, where we assume time is a dimension like space. But what if we stop doing that?
What if we built physics strictly on when information arrives?
If we stripped away the simultaneous grid and rebuilt our equations based only on the arrival times of signals, how much of our current understanding would crumble?
Would the Big Bang disappear? Would dark energy vanish?
Would the weirdness of quantum mechanics start to make sense? If we start pretending we can see the map and admit we're just reading the delayed reports, we might find out we're living in a very different universe than the one we think we are.
That is a provocative thought to end on. Next time you look up at the stars, or even just look across the room at a friend, remember, you aren't seeing them now. You're seeing who they were a fraction of a second ago.
We are always, inevitably, living in the past of everything around us.
Thanks for diving deep with us today.
Always a pleasure.
See you next time.